Imagine this. You are riding a beam of light. The universe rushes past at unimaginable speed. Clocks stop. Distances shrink. But can you actually exist like this, or would physics unravel you? Picture yourself moving at 299,792,458 meters per second. That is the speed of light, the cosmic speed limit that governs everything in our universe. This is not just any ordinary velocity. This is the boundary between what can exist and what cannot. Light itself travels as particles called photons, and these mysterious packets of energy always move at this exact speed. They never slow down, never speed up, never rest. But here is the question that will take us on an incredible journey. Could anything with mass, like a person, ever reach or ride alongside light? This is not just a physics problem. This is a journey into the very nature of space and time itself. When we explore what happens at the speed of light, we discover truths about reality that challenge everything we think we know about existence. The speed of light is not just fast. It is the fundamental constant that shapes the fabric of space-time. It determines how fast information can travel, how quickly cause can create effect, and ultimately, what it means to exist in our universe. Every second, light travels a distance that would take you nearly 8 laps around Earth. In 1 year, light covers nearly 6 trillion miles, a distance we call a light year. Yet even at this incredible pace, light from the nearest star takes over 4 years to reach us. But what would it feel like to move at such speed? What would you see? What would happen to your body, your mind, your very existence? These questions have puzzled scientists and dreamers for over a century, and the answers reveal some of the most beautiful and terrifying truths about our universe. When we chase light, we chase the edge of reality itself. We approach the boundary where time becomes meaningless, where space contracts to nothing, where the normal rules of existence simply break down. This is a realm where physics becomes philosophy, where science meets the deepest questions about what it means to be. The journey begins with understanding that light is not just something that illuminates our world. Light is the messenger of the universe, carrying information across vast cosmic distances. It connects distant stars to our eyes, ancient events to our present moment. Light is how the universe talks to itself. To explore this mystery, we must begin with the young mind who first imagined riding alongside a beam of light. A teenager whose simple question would revolutionize our understanding of space, time, and reality itself. In 1895, a curious 16-year-old student in Switzerland was walking home from school when an extraordinary thought struck him. Albert Einstein began to wonder what would happen if he could somehow catch up to a beam of light and travel alongside it. This simple question from a teenager's imagination would eventually reshape our entire understanding of the universe. Einstein pictured himself riding next to a light wave, moving at exactly the same speed as the electromagnetic radiation streaming through space. In his mind, he tried to visualize what this experience would be like. If he were traveling at the speed of light, what would the light wave beside him look like? Would it appear as a frozen wave, locked in place like a photograph of the ocean? According to everything Einstein had learned in physics class, if you were moving at the same speed as any wave, that wave should appear completely still to you. Just like if you were in a car driving alongside another car at exactly the same speed. The other car would appear motionless relative to you. So the light wave should look frozen, its electric and magnetic fields locked in place like a sculpture made of invisible energy. But this created a serious problem that troubled the young Einstein deeply. He knew from his studies that light was described by Maxwell's equations, the mathematical laws that governed all electromagnetic phenomena. These equations had been incredibly successful at explaining everything from radio waves to visible light, to the behavior of electric motors and generators. According to Maxwell's groundbreaking work, electromagnetic waves had to be oscillating, vibrating, constantly in motion. The electric and magnetic fields had to dance together in a specific rhythm as they traveled through space at incredible speeds. A frozen electromagnetic wave made no sense according to Maxwell's equations. It would be like trying to have a wave in water that never moved up and down, or a sound wave that never compressed and expanded the air around it. The mathematics simply did not allow for stationary electromagnetic fields arranged in a wave pattern. Such a configuration would violate the fundamental laws of electromagnetism that had been so carefully established and tested. This contradiction kept Einstein awake at night for months and years. Either Maxwell's equations were fundamentally wrong, which seemed impossible given how perfectly they described the electromagnetic world around us, or there was something deeply flawed about the way people thought about motion, space, and time themselves. Einstein spent years wrestling with this paradox, reading everything he could find about light and electromagnetism. He learned about the experiments that scientists were conducting to try to understand the true nature of light and its motion through space. Most physicists at the time believed that light waves needed some kind of medium to travel through, just like sound waves need air, and water waves need water to carry their energy from place to place. This hypothetical medium was called the luminiferous ether, an invisible substance that supposedly filled all of empty space throughout the entire universe. Scientists imagined the ether as a perfectly transparent, incredibly rigid, yet somehow massless material that could support the vibrations of light waves as they traveled across the cosmos from distant stars to our eyes on Earth. If the ether existed, then there would be one special reference frame in the universe where you would be truly at rest relative to this cosmic medium. In this frame, light would travel at its natural speed in all directions. But if you were moving through the ether, you should be able to detect your motion by measuring slight differences in the speed of light in different directions. But here was another puzzle that bothered Einstein and other thoughtful physicists of his time. Experiments kept failing to detect any sign of this mysterious ether. The most famous and carefully conducted attempt was the Michelson-Morley experiment, which tried to measure how fast Earth was moving through the ether by comparing the speed of light in different directions using incredibly precise interferometry techniques. The experimenters expected to find that light traveled slightly faster or slower depending on which direction it was going, just like you would measure different speeds for sound if you were moving through the air in an airplane or a car. When you move toward a sound source, the sound reaches you faster. When you move away, it takes longer to catch up. Instead, they found something completely unexpected and deeply puzzling. Light traveled at exactly the same speed in all directions, no matter which way Earth was moving in its orbit around the Sun. It was as if the speed of light was completely independent of the motion of the observer, which made no sense according to the physics of the time. This result was so strange that many scientists initially dismissed it or tried to explain it away with complicated theories about how the Earth might be dragging the ether along with it. Einstein realized that these experimental results might actually be pointing toward the solution to his thought experiment paradox. What if the speed of light really was constant for all observers, no matter how they were moving through space? What if there was no ether at all, and light simply traveled through empty space at a fixed speed that never changed regardless of the motion of its source or the person observing it? This idea seemed crazy at first, completely contrary to common sense and everyday experience. When you throw a ball from a moving train, the ball moves faster relative to the ground than it would if you threw it from a stationary platform. Why should light be any different? But Einstein followed the logic wherever it led, even when it challenged the most basic assumptions about how the world worked. If the speed of light was truly constant for all observers, then something else had to be flexible to make the mathematics work out correctly. Einstein realized that what had to change was not the light itself, but space and time themselves. These seemingly absolute unchanging aspects of reality would have to be relative, dependent on the motion of the observer. When you tried to catch up to a light beam, the light would not appear to slow down from your perspective. Instead, your own experience of space and time would change in just the right way to keep the speed of light constant. Time would slow down for you as you moved faster, and distances would shrink in the direction of your motion. These effects would be subtle at everyday speeds, completely unnoticeable in normal life, but they would become dramatic as you approached the speed of light. This was Einstein's breakthrough insight, the idea that would transform physics forever. Space and time were not fixed, unchanging backgrounds against which motion took place. They were dynamic, flexible aspects of reality that could stretch and compress, depending on how fast you were moving relative to other objects in the universe. Einstein worked out the mathematics of this new understanding and discovered something remarkable and beautiful. As your speed approached the speed of light, time would slow down more and more dramatically relative to stationary observers. At 50% the speed of light, time would pass at about 87% its normal rate. At 90% the speed of light, time would pass at less than half its normal rate. At 99% the speed of light, time would crawl to less than 1/7 its normal pace. And at exactly the speed of light, if such a thing were possible for massive objects, time would stop completely. Distances would undergo similar dramatic changes. In the direction of motion, lengths would contract more and more severely as speed increased. A spaceship traveling at 99% the speed of light would appear to be compressed to about 1/7 its normal length to a stationary observer, though the passengers inside would notice no change in their own ship. But this revealed the answer to Einstein's original thought experiment. You could not ride alongside a beam of light, because to do so would mean existing in a state where no time passes at all. Light itself exists in this timeless realm. From the moment a photon is created in the core of a star, to the moment it is absorbed by your eye after traveling across billions of miles of space, no time passes from the photon's perspective, even if that journey takes years from our point of view. Einstein realized that his teenage question had led him to discover something profound about the structure of reality itself. The speed of light was not just the fastest possible speed for light waves. It was the fundamental speed limit of the universe itself, the maximum rate at which any cause could create an effect, the boundary between the world of matter and energy that we experience and a timeless realm beyond normal existence. Light occupies this boundary because photons have no mass. Only massless particles can travel at the speed of light, and anything with mass must always travel slower. The closer you get to light speed, the more energy you need to go faster, and the energy required approaches infinity as you approach light speed. At exactly light speed, you would need infinite energy to maintain that motion, which is physically impossible. Einstein's simple thought experiment had revealed that space, time, matter, and energy are all interconnected in ways that no one had previously imagined. The universe operates according to principles far stranger and more beautiful than the mechanical clockwork that previous generations of scientists had envisioned. Reality itself is far more flexible and mysterious than anyone had dared to dream. Einstein's revelation about the nature of space and time opened up a whole new realm of questions that seemed almost like science fiction. If you could never actually reach the speed of light, what would happen as you got closer and closer to this cosmic boundary? What would you experience as you approached the edge of normal existence? The answers that emerged from Einstein's mathematics were more bizarre and wonderful than anyone could have imagined. As you accelerate toward the speed of light, the universe around you begins to transform in ways that challenge every assumption about reality. Time itself becomes your enemy and your ally. Space contracts and expands in impossible ways. and the very concept of existence takes on new meaning. These are not just theoretical possibilities or mathematical curiosities. They are real effects that have been measured and confirmed by countless experiments over more than a century of scientific investigation. Let us imagine that you are aboard a spacecraft capable of reaching incredible speeds, far beyond anything we can build today with our current technology. This imaginary vehicle can accelerate smoothly and safely to any fraction of light speed you desire, protected by some advanced shielding system that keeps you safe from the radiation and impacts that would normally destroy any real spacecraft at such velocities. As you begin to accelerate away from Earth, everything seems completely normal at first. The stars look exactly the same as they always have. Time passes at its usual comfortable rate, and you feel no different than you would in any ordinary vehicle traveling down a highway. Your coffee still tastes the same, your watch ticks at its normal pace, and your body functions exactly as it always has. But as your speed climbs higher and higher, approaching significant fractions of the speed of light, the universe begins to reveal its deepest and most carefully guarded secrets. The first strange effect you would notice is something called time dilation, one of the most profound and counterintuitive consequences of Einstein's theory of special relativity. As your spacecraft accelerates to higher and higher speeds, time itself begins to slow down for you relative to the people you left behind on Earth. This is not just a subjective feeling or an illusion created by your motion through space. Time literally passes more slowly for you than it does for stationary observers back home. At relatively modest speeds, this effect would be barely noticeable, almost lost in the noise of normal measurement uncertainties. At 10% the speed of light, which is still an enormous velocity of about 18,600 miles per second, time would pass at about 99.5% its normal rate. You might lose a few seconds over the course of a very long journey, hardly enough to matter in practical terms, or even to measure without extremely precise atomic clocks. But as your speed increases toward more significant fractions of light speed, the effect becomes more and more dramatic, following a mathematical curve that grows steeper and steeper as you approach the cosmic speed limit. At 20% light speed, time slows to about 98% its normal rate. At 30%, it drops to about 95%. The changes are still relatively small, but they are definitely measurable and meaningful. At 50% the speed of light, time would slow to about 87% its normal rate. A journey that took exactly 1 hour according to your onboard clocks would correspond to about 1 hour and 9 minutes passing on Earth. The difference is still not overwhelming, but it is definitely significant enough to notice and to cause practical problems for anyone trying to coordinate activities between your spacecraft and mission control back home. But watch what happens as you push closer and closer to the cosmic speed limit that governs all motion in the universe. The effects become more and more extreme, following a mathematical relationship that approaches infinity as your speed approaches the speed of light. At 70% the speed of light, time slows to about 71% its normal rate. At 80% light speed, time crawls to 60% its normal pace. At 90% the speed of light, time slows dramatically to just 44% its normal rate. Your hour now becomes 2 hours and 17 minutes for the people you left behind on Earth. They would age more than twice as fast as you during your journey. If you traveled for what felt like 1 year to you, more than 2 years would pass on Earth. The effect is becoming truly significant, creating a real separation between your timeline and the timeline of the rest of humanity. The effect becomes truly dramatic and almost unbelievable as you approach even closer to light speed. At 95% the speed of light, time slows to just 31% its normal rate. Your hour stretches to more than 3 hours on Earth. At 99% the speed of light, time crawls to less than 15% its normal rate. Your single hour corresponds to nearly 7 hours passing on Earth. You are aging 7 times more slowly than everyone you left behind. At 99.9% the speed of light, time slows to just 4.5% its normal rate, meaning your hour becomes 22 hours for stationary observers. At this speed, you could travel for what feels like a few months and return to find that many years have passed on Earth. The people you knew would be older, the world would have changed, and you would have become a time traveler visiting the future. This is not science fiction, or mathematical speculation, or some kind of thought experiment that exists only in the minds of theoretical physicists. Time dilation has been measured and confirmed in countless experiments using the most precise instruments that science can create. Particles called muons, created when high-energy cosmic rays from deep space strike atoms in the atmosphere high above Earth, normally decay so quickly that they should never be able to reach the surface of our planet. These unstable particles have a natural lifetime of only about 2 microseconds before they spontaneously decay into other particles. Even traveling at nearly the speed of light, they should only be able to travel about 600 meters before disappearing. Since they are created at altitudes of 10 to 15 kilometers above the surface, they should never make it all the way down to detectors on the ground. But because these muons are traveling at speeds very close to light speed, their internal clocks run slow compared to our clocks here on Earth. From our perspective, their lifetimes are extended by time dilation, and many of them survive long enough to be detected by instruments on the surface. The number that survive matches Einstein's predictions exactly, providing beautiful confirmation that time really does slow down for objects moving at relativistic speeds. Atomic clocks flown on commercial airplanes show measurable time differences compared to identical clocks left on the ground, exactly matching Einstein's predictions, even for the relatively modest speeds of jet aircraft. GPS satellites orbiting Earth must constantly correct for time dilation effects, or they would quickly accumulate errors large enough to make them useless for navigation. Every GPS device in your phone or car is a practical demonstration that Einstein was right about the nature of time. But time dilation is only part of the story of what happens as you approach light speed. As you accelerate toward this cosmic boundary, space itself begins to behave in equally strange and counterintuitive ways. Distances in the direction of your motion start to contract, shrinking like a compressed spring or accordion. This effect is called length contraction, and it becomes more and more severe as your speed increases toward the speed of light. From your perspective inside the spacecraft, everything seems completely normal. Your ship feels exactly the same size as it always has, and you notice no change whatsoever in your own body or the objects around you. Your cabin looks the same, your instruments read the same, and if you measure the length of your spacecraft with a ruler, you get exactly the same result you would have gotten when you were sitting still back on Earth. But to observers watching from Earth, your spacecraft appears to be getting shorter and shorter in the direction it is traveling. At 50% light speed, your ship would appear to be compressed to about 87% its original length. At 90% light speed, it would look like it had been squeezed down to just 44% its normal size. At 99% light speed, your ship would appear to outside observers as a thin sliver, compressed to less than 15% its rest length. These are not optical illusions or tricks of perspective caused by the finite speed of light or any kind of measurement error. Space really is contracting for objects moving at relativistic speeds. The distance between the front and back of your ship, as measured by stationary observers using perfectly accurate instruments, really has decreased. The physical space occupied by your spacecraft has been compressed in the direction of motion. Yet from your perspective inside the ship, nothing has changed at all. Even stranger, the distances to your destination begin to shrink as well from your perspective. If you were traveling to a star that was 10 light years away when you started your journey, that distance would appear shorter and shorter as your speed increased. At 90% light speed, the 10 light-year journey would appear to be only about 4.5 light-years from your perspective. At 99% light speed, it would seem like less than 1.5 light-years. The universe itself is contracting in the direction of your motion, making your journey seem shorter even as time slows down for you. But perhaps the most mind-bending aspect of approaching light speed is what happens to energy and mass. As your spacecraft accelerates faster and faster, it becomes harder and harder to make it go even faster. The energy required to continue accelerating increases dramatically as you approach the speed of light, following a mathematical curve that shoots toward infinity as you approach the cosmic speed limit. At 50% light speed, your ship would have about 15% more energy than when it was at rest. This extra energy has to come from somewhere, usually from the fuel you are burning or the propulsion system you are using. At 70% light speed, the total energy would be about 40% greater than at rest. At 90% light speed, it would have more than twice its rest energy. At 99% light speed, the energy would be 7 times greater than at rest. And at 99.9% light speed, the total energy would be over 22 times the rest energy. This extra energy manifests as what physicists call relativistic mass or relativistic momentum. Your spacecraft does not gain actual material substance or new atoms, but it behaves as if it had become much more massive and much more resistant to further acceleration. It becomes harder and harder to speed up, requiring more and more force to achieve smaller and smaller increases in velocity. The mathematics show that to reach exactly light speed would require infinite energy, which is impossible to obtain anywhere in the universe. This is why nothing with mass can ever reach or exceed the speed of light. But why is this cosmic speed limit so absolute? Why does the universe seem to go to such extraordinary lengths to protect this boundary? The answer reveals something profound about the very structure of reality itself. The speed of light is not just another velocity that happens to be very fast. It is not simply the fastest thing we have discovered, like a cosmic land speed record waiting to be broken by some future technology. Instead, the speed of light represents something much deeper and more fundamental about the way space and time are woven together into the fabric that physicists call space-time. To understand why light speed is so special, we need to think about the universe in a completely different way than our everyday experience suggests. We are used to thinking of space as a fixed background, like a stage upon which the drama of physics unfolds, and time as a universal clock that ticks at the same rate everywhere. But Einstein's insights revealed that space and time are actually connected in ways that make them inseparable from each other and from the matter and energy that move through them. Imagine space-time as a vast four-dimensional fabric that stretches across the entire universe. 3 of these dimensions correspond to the familiar directions of space that we can move through: forward and backward, left and right, up and down. The 4th dimension is time itself, woven into this fabric in such a way that space and time cannot be separated from each other. Every object in the universe, from the smallest particles to the largest galaxies, exists as a thread woven into this space-time fabric. When objects move through space, they are actually following paths through this 4-dimensional landscape. The faster an object moves through the spatial dimensions, the more slowly it moves through the time dimension, and vice versa. This is the deep reason behind time dilation and all the other strange effects of relativity. The speed of light represents the maximum possible slope that any path can have through this space-time fabric. It is the steepest angle at which any thread can be woven into the cosmic tapestry. Objects with mass must always follow paths that are less steep than this maximum angle, while massless particles like photons follow paths that lie exactly along this boundary. This geometric picture helps us understand why the speed of light is so absolute and universal. It is not just a speed limit imposed by some cosmic traffic cop. It is the fundamental structure of space-time itself. Asking why nothing can go faster than light is like asking why a circle cannot have corners, or why 2 + 2 cannot equal 5. It is not a limitation of our technology or our understanding. It is simply the way the universe is built. But the cosmic speed limit does more than just prevent objects from moving too fast. It also protects something even more fundamental: the relationship between cause and effect that makes logical sense of our universe. This relationship, which physicists call causality, depends critically on the existence of the light-speed barrier. Consider what would happen if something could travel faster than light. Imagine a spaceship that could somehow exceed this cosmic speed limit and travel from Earth to a distant star in less time than it takes light to make the same journey. From the perspective of some observers, this spaceship would arrive at its destination before it had actually left Earth. The effect would come before the cause, creating a logical paradox that would undermine the rational structure of physical law. Even worse, such faster-than-light travel could potentially allow information to be sent into the past. Using the strange effects of relativity, it might be possible to set up a communication system that could send messages backward in time, creating the possibility of paradoxes where effect comes before cause. You could potentially receive a message before it was sent, or even send a message to yourself in the past, warning about events that had not yet happened. The universe seems to have a built-in protection mechanism against such paradoxes. The speed of light barrier ensures that cause always comes before effect, that information cannot travel backward in time, and that the logical structure of physical law remains intact. By making it impossible for anything with mass to reach or exceed light speed, the universe preserves the rational order that allows science and logic to make sense of the world around us. This protection mechanism operates through the mathematical structure of Einstein's equations, which describe how space, time, matter, and energy all interact with each other. These equations contain within them the requirement that the speed of light must be constant for all observers, and this requirement automatically generates all the strange effects of relativity, including the infinite energy barrier that prevents massive objects from reaching light speed. The equations also reveal another profound truth about the nature of light speed. This cosmic velocity is not really about light at all. Light happens to travel at this speed because photons have no mass, but the fundamental speed limit exists independently of electromagnetic radiation. Even if light did not exist, the speed limit would still be there, built into the structure of space-time itself. Physicists sometimes call this fundamental velocity the speed of information, or the speed of causality rather than the speed of light, because it represents the maximum rate at which any cause can create an effect, or any information can travel from one place to another. It is the speed at which changes in the gravitational field propagate through space, the speed at which quantum entanglement operates, and the speed that governs all the deepest processes in the universe. This universal speed limit shows up in every area of physics, from the smallest scales of quantum mechanics to the largest scales of cosmology. Particles in accelerators approach this limit, but can never reach it, no matter how much energy is pumped into them. Gravitational waves, ripples in space-time itself, travel at exactly this speed. The expansion of the universe must respect this limit, and even the quantum vacuum fluctuations that fill empty space are governed by it. The mathematical beauty of this cosmic speed limit becomes even more apparent when we consider how it connects seemingly unrelated areas of physics. The same fundamental constant that limits the speed of particles also determines how electric and magnetic fields behave, how gravity propagates through space, and how quantum systems evolve over time. It is truly a universal constant that weaves together all the different forces and phenomena in nature. But why does this speed limit have the particular numerical value that it does? Why is the speed of light approximately 300 million meters per second rather than some other value? This question touches on some of the deepest mysteries in physics, related to the fundamental constants that determine the properties of our universe. The speed of light in empty space is determined by two other fundamental constants: the electric permittivity and magnetic permeability of the vacuum. These quantities describe how empty space itself responds to electric and magnetic fields, and their values determine how fast electromagnetic waves can propagate through the cosmic void. The speed of light emerges naturally from these deeper properties of space-time. Some physicists have speculated that these fundamental constants might have different values in other possible universes, leading to different cosmic speed limits. In a universe with a much lower speed limit, chemistry and biology might work very differently, or might not work at all. In a universe with a much higher speed limit, the strange effects of relativity would be much less noticeable, and the universe might seem more like the mechanical clockwork that earlier generations of scientists imagined. But in our universe, the cosmic speed limit has exactly the value it has, and this value determines everything about how matter, energy, space, and time interact with each other. It is the hidden parameter that governs the behavior of everything from atoms to galaxies, from the briefest quantum fluctuations to the longest cosmic epochs. The absoluteness of this speed limit also helps explain why the universe can seem so strange and counterintuitive to beings like us, who evolved to live at very low speeds compared to light. Our brains developed to understand a world where objects move at walking pace, or at most the speed of thrown rocks and running animals. In this low-speed world, space and time seem separate and absolute, and the strange effects of relativity are completely negligible. But as soon as we try to understand phenomena that occur at speeds approaching a significant fraction of light speed, our everyday intuition breaks down completely. We discover that space and time are relative, that simultaneity is not absolute, that mass and energy are interchangeable, and that the universe operates according to principles that seem to violate common sense. Yet these counterintuitive principles are not flaws in our understanding or limitations of our measurement techniques. They are fundamental features of the universe we live in, consequences of the deep geometric structure of space-time and the absolute nature of the cosmic speed limit. The universe really does work this way, whether it seems reasonable to us or not. The cosmic speed limit also has profound implications for our place in the universe and our ability to explore and understand it. It means that information about distant events can only reach us at light speed, so we can never know what is happening right now in faraway places. When we look at distant stars and galaxies, we are always seeing them as they were in the past, not as they are today. This creates a kind of cosmic horizon beyond which we can never see, no matter how powerful our telescopes become. The observable universe has a finite size, determined by how far light has been able to travel since the beginning of time. Beyond this horizon, there might be infinite expanses of space and countless other galaxies, but we can never observe them directly because their light has not had enough time to reach us. The speed limit also means that interstellar travel will always be incredibly challenging, even with the most advanced technology we can imagine. While it might be possible to build spacecraft that approach light speed, the energy requirements become astronomical, and the time dilation effects mean that such journeys would create permanent separation between travelers and the civilizations they leave behind. The cosmic speed limit raises a fascinating question about light itself. If nothing with mass can reach the speed of light, what is it like for the massless particles that actually travel at this ultimate velocity? What does the universe look like from the perspective of a photon racing through space at the maximum possible speed? The answers reveal some of the most profound and mysterious aspects of reality. To understand the experience of light, we must first grasp something that seems almost impossible to believe. From the perspective of a photon, no time passes at all during its journey, no matter how far it travels or how long that journey takes from our point of view. A photon emitted by a star billions of light years away experiences its entire cosmic voyage as a single, timeless instant. From emission to absorption, from creation to destruction, the photon exists in a realm where time has no meaning. This is not merely a strange consequence of relativity theory or an abstract mathematical result. It is a fundamental feature of how the universe works at the deepest level. When we calculated earlier how time slows down for objects approaching light speed, we saw that time dilation becomes more and more extreme as velocity approaches the cosmic speed limit. At 99% light speed, time slows to less than 15% its normal rate. At 99.9%, it slows to less than 5%. As the speed approaches exactly the speed of light, time slows down more and more until it stops completely. For a photon traveling at exactly light speed, time dilation becomes infinite. The passage of time, as measured by any outside observer, becomes completely divorced from the photon's own internal experience. What we observe as a journey lasting billions of years unfolds as a single moment from the photon's perspective. The entire lifetime of the photon, from the nuclear reaction that created it in the core of a distant star, to the moment it strikes a detector on Earth, occupies zero time in the photon's reference frame. This creates a picture of light that is both beautiful and deeply strange. Every photon in the universe exists in a timeless state, connecting distant events across space without experiencing the passage of time between them. Light serves as an instantaneous messenger, carrying information across cosmic distances while existing outside the normal flow of temporal experience that governs everything else in the universe. But this timeless nature of light creates a profound puzzle when we try to understand what the universe looks like from a photon's perspective. In Einstein's theory of relativity, we can always ask what events look like from the reference frame of any moving object. We can imagine ourselves riding along with a spacecraft, a planet, or even a subatomic particle, and we can calculate what that observer would see and experience. However, when we try to apply this same approach to a photon, something remarkable happens. The mathematics breaks down completely. There is no valid reference frame for a photon. We cannot meaningfully ask what the universe looks like from the perspective of light itself, because such a perspective does not exist within the framework of physics. This is not simply a limitation of our current understanding or a problem that might be solved with better mathematics. It is a fundamental feature of the structure of space-time itself. Objects traveling at light speed do not have reference frames in the same sense that slower-moving objects do. The concept of a photon's perspective is literally meaningless within the context of Einstein's theory. To understand why this is the case, we need to think carefully about what we mean by a reference frame. In physics, a reference frame is a coordinate system from which we can measure positions, velocities, and the passage of time. Every valid reference frame must have certain mathematical properties that allow the laws of physics to be formulated consistently within that frame. One of the most important requirements is that time must pass at a finite, non-zero rate within any valid reference frame. There must be a meaningful way to define simultaneity, to order events in time, and to measure durations and intervals. But for an object traveling at light speed, time dilation becomes infinite, which means that the rate of time passage becomes zero. This violates the basic mathematical requirements for a valid reference frame. Another way to understand this is through the concept of proper time, which is the time measured by a clock traveling along with an object. For any object moving slower than light speed, proper time provides a meaningful way to parameterize the object's journey through space-time. But for a photon, the proper time between any two events is always zero, regardless of the spatial distance traveled. This makes it impossible to define a consistent timeline or to establish causal relationships within the photon's supposed reference frame. The absence of a photon reference frame has profound implications for how we think about the nature of light and its role in the universe. It means that photons exist in a fundamentally different category from all other objects. While massive particles experience the flow of time and have perspectives from which they can observe the universe, photons exist in a timeless realm that is completely disconnected from the temporal experience that defines normal existence. This timeless nature of light helps explain some of the most mysterious aspects of quantum mechanics and the behavior of electromagnetic radiation. When a photon is created in one location and absorbed in another, there is no intervening time period during which the photon exists as a traveling object. From the photon's perspective, creation and absorption are the same event happening at the same instant. This creates a picture of electromagnetic radiation that is very different from our everyday intuition about traveling objects. We tend to think of light as consisting of particles that move through space over time, like tiny bullets fired from a gun. But the reality is stranger and more subtle. Photons exist as connections between events, linking moments of emission with moments of absorption across space, without experiencing the journey between them. Consider a photon emitted by the sun and absorbed by a leaf on Earth 8 minutes later. From our perspective, the photon travels 93 million miles through space, crosses the vacuum between star and planet, and carries energy from one location to another. But from the photon's timeless perspective, the nuclear reaction in the sun's core and the photosynthetic process in the leaf are the same event, connected instantaneously across space. This timeless connection helps explain some of the most puzzling features of quantum mechanics, particularly the phenomenon of quantum entanglement. When two particles become entangled, they maintain an instantaneous connection regardless of the distance between them. Changes to one particle instantly affect the other, even if they are separated by billions of miles. This connection operates at light speed, the maximum rate at which information can travel. But from the perspective of the light speed signals that maintain the entanglement, no time passes during the transmission. The absence of a photon reference frame also illuminates the deep connection between light and the structure of space-time itself. Photons follow what physicists call null geodesics, paths through space-time that have zero length in the four-dimensional geometry of space and time. These paths define the boundary between regions of space-time that can influence each other and regions that cannot. Every event in space-time is surrounded by a light cone, a three-dimensional surface that represents all the possible paths that light signals can take to or from that event. Events inside your past light cone can potentially influence you because light from those events has had time to reach your location. Events inside your future light cone can potentially be influenced by you because light from your current location has time to reach them. But events outside both light cones are causally disconnected from you, unreachable by any signal traveling at or below light speed. These light cones, defined by the paths that photons can take through space-time, determine the causal structure of the entire universe. They establish which events can influence which other events, and they create the network of cause and effect relationships that gives meaning to physical law. In a very real sense, photons and their timeless journeys define the logical structure of reality itself. The timeless nature of light also has implications for our understanding of the quantum nature of electromagnetic radiation. When we try to apply quantum mechanics to photons, we discover that they behave in ways that are fundamentally different from massive particles. Photons cannot be localized in space in the same way that electrons or protons can be. They exist as excitations of the electromagnetic field that extends throughout all of space. This field-theoretic picture of light is consistent with the absence of a photon reference frame. Rather than thinking of photons as discrete particles traveling through space, we can think of them as ripples in a universal electromagnetic field. These ripples propagate at light speed, connecting distant regions of the field instantaneously from their own timeless perspective. The mathematical description of electromagnetic radiation reflects this timeless nature. Maxwell's equations, which govern all electromagnetic phenomena, are written in a form that treats space and time symmetrically. The equations describe how changes in electric and magnetic fields propagate through space-time at exactly light speed, creating self-sustaining waves that can travel indefinitely without any medium to support them. These electromagnetic waves carry energy and momentum, but they do not experience the passage of time during their propagation. They exist as connections between the sources that create them and the detectors that absorb them, linking cause and effect across arbitrary distances of space without any intervening temporal experience. Understanding the timeless nature of light also helps explain why the speed of light plays such a fundamental role in physics beyond just electromagnetic theory. This cosmic speed limit appears in the equations of quantum mechanics, general relativity, thermodynamics, and virtually every other area of theoretical physics. It is not just the speed at which light happens to travel, but the fundamental rate at which causality operates throughout the universe. The absence of time in the photon's experience creates a unique perspective on the nature of existence itself. While every massive object in the universe experiences the flow of time and exists within a temporal framework, photons exist in an eternal present moment that connects all of space instantaneously. They are the universe's way of maintaining causal connections across vast distances without the burden of temporal experience. Now that we understand why photons exist in a timeless realm and why nothing with mass can actually reach light speed, we can explore a more personal question. What would happen to you as a human being if you could somehow approach very close to this cosmic speed limit? What would your body experience? How would your perception of the universe change? And what practical challenges would you face during such an incredible journey? The answers paint a picture that is both fascinating and terrifying, revealing how the extreme physics of relativistic travel would transform every aspect of your existence. From the moment you began accelerating toward light speed, your relationship with time, space, energy, and even your own biology would begin to change in ways that challenge our deepest assumptions about what it means to be human. Let us imagine that you are aboard an advanced spacecraft capable of accelerating smoothly and safely to extremely high speeds. This imaginary vehicle has somehow solved all the enormous engineering challenges that would make such a journey impossible with current technology. It has an incredibly powerful propulsion system, perfect radiation shielding, and artificial gravity systems that protect you from the crushing forces of acceleration. As your spacecraft begins its journey and your speed climbs to 10% of light speed, you would still feel relatively normal. At this velocity, you would be traveling at about 18,600 miles per second, fast enough to circle the Earth in less than 14 seconds. Yet the relativistic effects would still be quite small. Time would pass at about 99.5% its normal rate, hardly noticeable without extremely precise instruments. But as your speed continues to increase toward more significant fractions of light speed, the effects become increasingly dramatic and impossible to ignore. At 50% light speed, time aboard your spacecraft would slow to 87% its normal rate compared to Earth. If you looked at a clock on Earth through your telescope, you would see it running noticeably faster than your own clocks. Every hour that passes for you corresponds to about 1 hour and 9 minutes passing on Earth. The biological implications of this time dilation would be subtle but significant. Your metabolism, your heart rate, your brain activity, and every other biological process would slow down proportionally. You would age more slowly than the people you left behind on Earth, but you would not notice this change yourself, because your perception of time would slow down by exactly the same amount. From your perspective, everything would seem completely normal. At 75% light speed, time would slow to about 66% its normal rate. Your hour now corresponds to about an hour and 30 minutes on Earth. At this speed, the energy requirements for further acceleration are becoming enormous, requiring increasingly powerful propulsion systems and vast amounts of fuel or energy storage. When you reach 90% of light speed, the effects become truly dramatic. Time slows to just 44% its normal rate, meaning that every hour you experience corresponds to more than 2 hours passing on Earth. If you maintained this speed for what felt like 1 year to you, more than 2 years would pass for everyone back home. You would return to find that the world had aged faster than you had, that technology had advanced, that people had grown older, and that you had become a time traveler visiting your own future. The energy content of your spacecraft at this speed would be more than twice what it was when you were at rest. This extra energy manifests as increased inertia, making it much harder to accelerate further or to change direction. Your spacecraft would behave as if it had become much more massive, requiring enormous forces to achieve even small changes in velocity. At 95% light speed, time slows to just 31% its normal rate. You are now aging more than 3 times slower than everyone on Earth. The energy requirements for maintaining this speed are astronomical, and the energy needed to go even faster approaches infinity. Your spacecraft contains more than 3 times its rest energy, stored in the form of kinetic energy that makes every atom in your body and your ship behave as if it were much more massive than normal. But perhaps the most dramatic change would occur at 99% light speed, where time slows to less than 15% its normal rate. Every hour you experience now corresponds to nearly 7 hours passing on Earth. If you traveled at this speed for what felt like 1 month to you, more than half a year would pass for the people you left behind. You would be aging 7 times more slowly than the rest of humanity. At this extreme speed, the energy content of your spacecraft would be 7 times greater than its rest energy. The amount of energy required to accelerate to this velocity would be staggering, equivalent to converting substantial amounts of matter directly into energy through nuclear processes. Even tiny increases in speed beyond this point would require enormous additional energy inputs. But these mathematical descriptions of time dilation and energy only hint at what the experience would actually be like for you as a conscious observer. As you approached these extreme speeds, you would notice dramatic changes in how the universe appeared around you. The phenomenon called relativistic beaming would cause the light from stars and galaxies to appear redistributed in strange and beautiful ways. Light from objects ahead of you would be blue-shifted to higher frequencies and greater intensities. Visible light from stars in front of your spacecraft would shift into ultraviolet frequencies. Ultraviolet light would become X-rays, and X-rays would become gamma rays. This high-energy radiation would be focused into an increasingly narrow cone directly ahead of your ship, creating a brilliant searchlight effect that would make forward objects appear much brighter and bluer than normal. Meanwhile, light from objects behind you would be red-shifted to lower frequencies and dimmer intensities. Visible light would shift into infrared. Infrared would become radio waves, and radio waves would be stretched to even longer wavelengths. Objects behind you would appear redder and dimmer, eventually fading from view entirely as their light was shifted beyond the range of your instruments. At very high speeds, most of the visible universe would appear to compress into a brilliant circular region directly in front of your spacecraft. This cosmic headlight effect would make it look as if you were traveling through a tunnel of intensely bright blue-shifted starlight, while the rest of the universe faded into darkness behind you. the familiar constellations would be completely unrecognizable, compressed and distorted by the extreme effects of relativistic aberration. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space with a nearly uniform glow of radio waves, would also appear dramatically distorted. In the direction you are traveling, this background radiation would be blue shifted into visible light and beyond, contributing to the brilliant glow ahead of your ship. Behind you, it would be red shifted to even longer radio wavelengths, becoming nearly undetectable. These visual effects would be accompanied by an equally dramatic transformation in your perception of distances and travel times. Due to length contraction, the distances to your destination would appear to shrink dramatically as your speed increased. A journey to a star 10 light years away would appear to be only about 1.5 light years from your perspective when traveling at 99% light speed. This creates a remarkable symmetry between time dilation and length contraction. Although time passes more slowly for you, the distances you need to travel appear shorter, so the trip still takes a reasonable amount of time from your perspective. You might reach distant stars in what feels like months or years, rather than the decades or centuries that would pass on Earth during your journey. However, the biological and physical stresses of such extreme travel would present enormous challenges that go far beyond the mathematical descriptions of relativity. Even with perfect shielding and life support systems, your body would face unprecedented conditions that could threaten your survival in unexpected ways. The radiation environment at near light speeds would be incredibly hostile. Even tiny particles of cosmic dust, normally harmless, would strike your spacecraft with the energy of high-speed bullets. Individual atoms in the thin gas between stars would hit your ship with the force of particle accelerator beams. Your shielding systems would need to be far more advanced than anything we can currently imagine to protect you from this constant bombardment of high-energy particles. The acceleration required to reach these extreme speeds would also present enormous challenges for human physiology. Even if you could somehow spread the acceleration over many months or years to keep the forces manageable, your body would need to endure prolonged periods of stress that could have unpredictable effects on your health and mental state. Perhaps most challenging of all would be the psychological impact of such extreme isolation and temporal displacement. As you traveled at near light speeds, you would become increasingly disconnected from the timeline of human civilization. Communication with Earth would become virtually impossible due to the extreme time dilation effects. Messages that took minutes to send would arrive years later from Earth's perspective, making any kind of meaningful dialogue completely impractical. You would essentially become unstuck in time, existing in your own accelerated timeline, while the rest of humanity aged and changed at a rate you could barely comprehend. When you finally return to Earth, you might find that centuries or millennia had passed, that the civilization you left behind had evolved beyond recognition, and that you had become a visitor from the distant past, arriving in an unimaginably different future. The visual transformation of the universe at near light speeds creates one of the most spectacular and mind-bending aspects of relativistic travel. As we explored in the previous chapter, the cosmic headlight effect would compress most of the visible universe into a brilliant tunnel of light ahead of your spacecraft. But let us dive deeper into this incredible visual journey and explore exactly what you would see as you pushed closer and closer to the ultimate speed limit. The changes would begin subtly at lower speeds, then accelerate into a crescendo of cosmic beauty and strangeness as you approached light speed itself. Understanding these visual effects requires us to think carefully about how light behaves when observed from different reference frames, and how the fundamental properties of electromagnetic radiation change when viewed by observers moving at relativistic speeds. At modest speeds, perhaps 20 to 30% of light speed, you would begin to notice the first hints of relativistic aberration. This effect causes the apparent positions of stars and other light sources to shift slightly in the direction of your motion. It is similar to the way rain appears to come at you from an angle when you are driving in a car, even though the rain is actually falling straight down. Light from stars would appear to be coming from slightly ahead of their true positions, as if the entire universe were tilting forward in the direction of your travel. As your speed increased to 50% of light speed, this aberration effect would become much more pronounced. Stars that were originally visible to your left and right would appear to move forward, clustering more and more toward the direction you were traveling. The constellations you knew from Earth would begin to lose their familiar shapes as individual stars shifted their apparent positions in complex patterns determined by the mathematics of special relativity. Simultaneously, you would start to notice dramatic changes in the colors and brightness of stars in different directions. The Doppler effect, which causes the frequency of light to change when the source and observer are moving relative to each other, would begin to dominate your visual experience. Stars ahead of you would appear bluer and brighter as their light was shifted to higher frequencies. Stars behind you would appear redder and dimmer as their light was stretched to lower frequencies. At 75% light speed, these color shifts would become extreme and spectacular. Stars directly ahead of you would no longer appear as ordinary white or colored points of light. Their visible light would be shifted far into the blue and beyond, into ultraviolet frequencies that your eyes could not detect directly. However, their ultraviolet and X-ray emissions would be shifted down into the visible range, potentially making them appear as brilliant blue-white or even purple sources of light. The effect would be like watching the universe through a cosmic prism that separated different types of electromagnetic radiation and redistributed them across the spectrum. Radio emissions from distant galaxies would be shifted up into infrared and visible light. Infrared radiation would become visible. Visible light would shift into ultraviolet, and ultraviolet and X-ray emissions would be boosted to even higher energies, potentially creating gamma-ray radiation of incredible intensity. Meanwhile, the view behind you would be undergoing an equally dramatic but opposite transformation. Stars and galaxies in your wake would be losing their visible light as it was stretched into infrared and radio wavelengths. The brilliant tapestry of the night sky would gradually fade to a dim red glow, then disappear entirely as the light was redshifted beyond the range of human vision. Looking backward, you might see only darkness punctuated by the occasional faint red dot marking the location of what had once been a brilliant star. At 90% light speed, the visual effects would reach levels of intensity that would challenge the limits of human perception and perhaps even threaten your safety. The relativistic beaming effect would concentrate most of the electromagnetic radiation in the universe into a narrow cone directly ahead of your spacecraft. This cosmic searchlight would contain not just visible light, but also high-energy ultraviolet, X-rays and gamma rays that had been Doppler shifted down from even more energetic sources. The intensity of this forward radiation would be extraordinary, potentially millions of times brighter than the ordinary starlight you were accustomed to seeing. Your spacecraft would need incredible shielding systems, not just to protect you from physical impacts, but also to filter this intense electromagnetic radiation and prevent it from cooking you alive. Special optical systems would be required to step down the intensity and frequency of the light to levels that human eyes could safely observe. Through such protective systems, you might see a view that resembled traveling through a tunnel of pure light. The walls of this tunnel would be formed by the aberrated and Doppler shifted light from billions of stars and galaxies, all compressed into a relatively narrow field of view directly in front of you. The colors would be unlike anything visible from Earth, dominated by intense blues, violets, and perhaps colors corresponding to frequencies that human eyes cannot normally detect. At the same time, your view to the sides and behind would be almost completely dark. The relativistic aberration effect would have moved almost all sources of light into the forward direction, leaving the rest of space nearly empty of visible illumination. You would be flying through a universe that appeared to have collapsed into a brilliant tunnel of light ahead, and darkness everywhere else. But the most dramatic visual effects would occur at 99% light speed and beyond, where the mathematics of relativity create truly extraordinary transformations of space and time. At these extreme velocities, the forward light cone would narrow to just a few degrees, concentrating virtually all the visible radiation in the universe into an incredibly intense beam directly ahead of your spacecraft. The energy density of this forward radiation would be so high that it would contain gamma rays, with energies far exceeding anything produced by the most violent cosmic events. These would be photons that started as ordinary starlight but had been blue, shifted to such extreme frequencies that they carried the energy of cosmic ray particles. Your shielding systems would need to handle radiation levels that would make the core of a nuclear reactor seem mild by comparison. If you could somehow observe this forward radiation safely, you would see the entire visible universe compressed into a brilliant disk ahead of you. This disk would contain the light from billions of galaxies, all blue shifted and concentrated into a region that might appear no larger than the full moon appears from Earth. The intensity would be so great that it would appear as a blazing white or blue-white circle that would dominate your entire forward field of view. Within this disk, you might be able to distinguish individual features corresponding to distant galaxies and galaxy clusters, but they would appear compressed and distorted by the extreme effects of relativistic aberration. The familiar shapes of spiral and elliptical galaxies would be unrecognizable, stretched and compressed into patterns that reflected the strange geometry of space and time at near light speeds. Perhaps most remarkably, this compressed view would represent a kind of time machine, showing you light from cosmic events spanning billions of years of cosmic history. Because you would be catching up to light that left distant galaxies at different times in the past, you would be seeing a compressed timeline of cosmic evolution, light from the most distant visible galaxies, showing them as they appeared when the universe was young, would be mixed with light from nearer galaxies, showing more recent cosmic epochs. The cosmic microwave background radiation, normally invisible to human eyes, would also contribute to this spectacular display. This radiation, the afterglow of the Big Bang itself, would be blue shifted from radio frequencies up into visible light and beyond. You might actually be able to see the edge of the observable universe as a brilliant glow mixed with the light from distant galaxies, creating a visual representation of the cosmic horizon that normally lies far beyond human perception. As your speed approached even closer to light speed, at 99.9% or beyond, this forward disk of light would become narrower and more intense. At some point, it might narrow to such a small angular size that it would appear almost like a single brilliant star ahead of you, containing within its compressed image the light from the entire visible universe. Behind you, the view would be one of almost complete darkness. The few photons that managed to reach you from the rear would be so extremely red-shifted that they would have wavelengths measured in meters or even kilometers, far beyond the range of any conceivable detection system. You would be flying through what appeared to be an empty void, chasing a brilliant beacon of compressed starlight that represented the sum total of all electromagnetic radiation in the cosmos. The experience would be like flying through a cosmic tunnel where the walls were made of pure darkness, and the end was marked by a blazing circle of light that contained every star, every galaxy, and every photon in the visible universe. It would be the ultimate expression of the relativistic universe, where space and time conspired to compress all of cosmic history into a single, brilliant point ahead of your spacecraft. But even this incredible visual spectacle would pale in comparison to what would happen if you could somehow approach even closer to light speed. At velocities differing from light speed by only tiny fractions, the forward light cone would narrow to almost nothing. concentrating energies so vast that they would challenge the very limits of what matter and energy can do within the framework of known physics. The universe would become a place of such extreme beauty and violence that it would transcend normal categories of human experience. You would be witnessing the cosmos itself, compressed into forms that revealed its deepest mathematical structure, seeing patterns and relationships that could never be observed from any ordinary reference frame, moving at normal speeds through space and time. After exploring the incredible effects that would occur as you approach light speed, a fundamental question emerges. Can anything in the universe actually travel at this ultimate velocity? We have seen that massive objects like spacecraft and human beings can never quite reach light speed. But what about the particles and phenomena that do achieve this cosmic speed limit? Understanding what can and cannot travel at light speed reveals some of the deepest principles governing our universe. The answer begins with a fundamental distinction in physics between particles that have mass and particles that are massless. This distinction determines everything about how objects can move through space and time, and it creates two completely different categories of existence in our universe. Massive particles can never reach light speed, while massless particles can never travel at any other speed. Let us start with the particles that we know definitely travel at light speed. The most familiar of these are photons, the particles of light and all other forms of electromagnetic radiation. Every photon in the universe, whether it carries radio waves, visible light, X-rays, or gamma rays, travels at exactly the same speed through empty space. 299,792,458 meters per second. This speed is absolutely constant for all photons, regardless of their energy, frequency, or the motion of their source. A low-energy radio photon travels at exactly the same speed as a high-energy gamma-ray photon. Light from a flashlight travels at the same speed as light from a distant quasar. Photons emitted by a spacecraft moving toward you at high speed travel at the same speed as photons emitted by a spacecraft moving away from you. The speed of light is truly universal and unchanging. But photons are not the only particles that travel at light speed. In the theoretical framework of particle physics, any particle that has zero mass must travel at light speed. This includes gluons, the particles that carry the strong nuclear force and hold the protons and neutrons in atomic nuclei together. Gluons are confined within protons and neutrons and cannot travel freely through space like photons. But when they do move, they must travel at exactly light speed. Gravitational waves, ripples in the fabric of space-time itself, also propagate at light speed. These waves are created when massive objects accelerate, such as when two black holes spiral into each other or when neutron stars collide. The waves travel outward from their source at exactly light speed, carrying information about the gravitational disturbance across the cosmos. Recent detections of gravitational waves by instruments like LIGO have confirmed that these space-time ripples do indeed travel at the predicted velocity. The pattern is clear. Anything massless must travel at light speed, and anything with mass cannot reach light speed. This is not an arbitrary rule imposed by nature, but a direct consequence of the mathematical structure of space-time as described by Einstein's theory of relativity. The equations that govern motion through space and time simply do not allow any other possibilities. To understand why this is the case, we need to think about energy and momentum in relativistic physics. For any object with mass, the total energy includes both the rest energy, which comes from the mass itself, and the kinetic energy, which comes from motion. As the object moves faster, the kinetic energy increases, but so does the effective mass, making it harder and harder to accelerate further. The mathematical relationship shows that as velocity approaches light speed, the energy required for further acceleration approaches infinity. It would take infinite energy to accelerate any massive object to exactly light speed, which is impossible to achieve anywhere in the universe. This energy barrier is absolute and cannot be overcome by any conceivable technology or natural process. For massless particles, the situation is completely different. They have no rest energy, so all their energy comes from their motion. The mathematics of relativity requires that such particles must always move at light speed. They cannot be slowed down or sped up, and they cannot exist at rest. From the moment they are created, they travel at light speed until the moment they are absorbed or destroyed. This creates a fascinating dichotomy in the universe. Massive particles exist in a realm where time passes, where motion through space is possible at various speeds, and where objects can be at rest or in motion relative to each other. Massless particles exist in a timeless realm, where only one speed is possible, where rest is impossible, and where the normal concepts of temporal experience do not apply. The experimental evidence for these principles is overwhelming and has been confirmed in countless ways over more than a century of scientific investigation. Particle accelerators around the world routinely accelerate electrons, protons, and other massive particles to speeds approaching light speed, but they can never quite reach it. The closer they get, the more energy is required for even tiny additional increases in speed. At the Large Hadron Collider, protons are accelerated to 99.9999% of light speed. Even at this incredible velocity, just a tiny fraction below the cosmic speed limit, the protons still have not reached light speed. To go faster would require exponentially more energy, and to reach exactly light speed would require infinite energy, confirming Einstein's predictions with extraordinary precision. Meanwhile, every measurement of light speed, whether using lasers, radio waves, or astronomical observations, confirms that electromagnetic radiation travels at exactly the same velocity in all reference frames. This constancy of light speed, independent of the motion of source or observer, is one of the most precisely verified facts in all of physics. The behavior of unstable particles provides another beautiful confirmation of relativistic principles. Particles called muons are created when cosmic rays strike the upper atmosphere about 10 to 15 kilometers above Earth's surface. These particles have a natural lifetime of about 2 microseconds before they decay into other particles. At the speed of light, 2 microseconds would allow muons to travel only about 600 meters before decaying. Since they are created much higher than this, basic physics would suggest that none of them should reach the ground. Yet muon detectors on Earth's surface routinely detect these particles, providing direct evidence of time dilation. The muons are traveling at speeds very close to light speed, typically above 90% of the cosmic speed limit. At these velocities, time dilation extends their lifetimes, as measured from our reference frame. What appears to be 2 microseconds in the muon's reference frame corresponds to much longer periods in our reference frame, allowing the particles to survive long enough to reach Earth's surface. This experiment, which occurs naturally in our atmosphere every day, provides continuous confirmation that massive particles can approach but never reach light speed, and that the effects of relativity are exactly as Einstein predicted. The number of muons detected matches the theoretical predictions with remarkable accuracy. The distinction between massive and massless particles also helps explain some of the most fundamental forces and interactions in nature. The electromagnetic force is carried by massless photons, which is why electromagnetic effects can propagate instantly at light speed across arbitrary distances. Electric and magnetic fields can influence distant objects because the photons that carry this influence travel at the maximum possible speed through spacetime. The weak nuclear force, responsible for certain types of radioactive decay, is carried by particles called W and Z bosons. These particles have mass, which means they cannot travel at light speed and have limited range. This is why the weak force only operates over very short distances within atomic nuclei, unlike the electromagnetic force, which can act across vast cosmic distances. The strong nuclear force, which holds protons and neutrons together in atomic nuclei, is carried by massless gluons. However, these gluons are confined within protons and neutrons by the peculiar properties of quantum chromodynamics, the theory that describes the strong force. While gluons themselves are massless and would travel at light speed if free, they are trapped within particles and cannot propagate freely through space. Gravity, according to Einstein's theory of general relativity, propagates through gravitational waves that travel at light speed. This means that gravitational effects, like electromagnetic effects, can influence distant objects at the maximum possible speed. If the Sun suddenly disappeared, we would continue to orbit its gravitational field for about 8 minutes, the time it takes for the gravitational waves carrying this information to reach Earth. The absolute nature of the light speed barrier also has profound implications for our understanding of causality and information transfer in the universe. Nothing can carry information faster than light speed, which means that cause and effect relationships are protected by this cosmic speed limit. Events can only influence other events if they are connected by paths that respect the light speed limit. This creates a kind of cosmic communication network where information flows through the universe at exactly light speed, carried by photons, gravitational waves, and other massless phenomena. The speed of light is not just the speed of electromagnetic radiation, but the fundamental speed of information itself, the rate at which the universe can coordinate cause and effect relationships across space. Understanding what can and cannot travel at light speed also illuminates the deep connection between mass, energy, space, and time in Einstein's universe. Mass is not just a measure of how much matter an object contains, but a fundamental property that determines how that object can move through space-time. Objects with mass are forever confined to speeds below light speed, while massless entities exist in the timeless realm of light speed itself. This dichotomy creates two different types of existence in our universe: the temporal realm of massive objects, where time passes and motion is possible at various speeds, and the timeless realm of massless phenomena, where only light speed is possible and temporal experience has no meaning. The boundary between these realms is the speed of light itself, the cosmic divide that separates ordinary existence from the strange physics of the ultimate speed limit. Having established that nothing with ordinary mass can reach light speed, and that massless particles must always travel at light speed, we encounter one of the most intriguing and controversial concepts in theoretical physics: tachyons. These hypothetical particles would represent a third category of matter, objects that always travel faster than light and can never slow down to light speed or below. While no tachyons have ever been detected, their mathematical possibility reveals fascinating insights about the structure of space-time and the fundamental limits of physical reality. The word tachyon comes from the Greek word tachys, meaning swift or fast. These theoretical particles were first seriously considered by physicists in the 1960s as a mathematical curiosity that emerged from the equations of special relativity. When you solve Einstein's equations for motion through space-time, 3 distinct solutions appear, corresponding to 3 different types of particles, based on their relationship to the cosmic speed limit. The first type includes all ordinary matter, particles with positive mass that must always travel slower than light speed. These are called bradyons, from the Greek word brades, meaning slow. This category includes everything we are familiar with, from electrons and protons to planets and galaxies. Bradyons can exist at rest and can be accelerated to high speeds. but they can never reach or exceed light speed. The second type includes massless particles that must always travel at exactly light speed. These are sometimes called luxons, from the Latin word lux meaning light. This category includes photons, gluons, and gravitational waves. Luxons cannot exist at rest and cannot be slowed down or sped up from their constant velocity of light speed. The third type, the tachyons, would have what physicists call imaginary mass and would be required to always travel faster than light speed. Just as bradyons cannot reach light speed from below, tachyons could never slow down to light speed from above. They would exist in a realm of faster than light motion, forever separated from the ordinary world of slower than light particles. The mathematics that describes tachyons is both elegant and deeply strange. When you plug faster than light velocities into Einstein's equations, the mathematical expressions that normally describe energy and momentum become complex numbers involving the square root of negative quantities. This imaginary mass does not mean that tachyons would be figments of imagination, but rather that their mass would be described by imaginary numbers in the mathematical sense. For a tachyon, the faster it travels, the less energy it has. This is exactly opposite to the behavior of ordinary particles, which require more and more energy to go faster. A tachyon with infinite speed would have zero energy, while a tachyon traveling just barely faster than light speed would have infinite energy. This creates the paradoxical situation where tachyons would lose energy as they speed up and gain energy as they slow down. Even stranger, the direction of time would appear reversed for tachyons compared to ordinary matter. From the perspective of normal observers, tachyons would appear to move backward in time, arriving at their destination before they left their origin. This creates the potential for causality violations that would undermine the logical structure of physical law. Consider what would happen if tachyons could carry information faster than light. You could potentially send a message to a distant location that would arrive before you sent it, at least from the perspective of some observers. Using the relativity of simultaneity, it might even be possible to arrange for tachyon signals to arrive in the past of the sender, creating the possibility of paradoxes where effects precede their causes. These causality problems are so severe that most physicists believe tachyons cannot exist in reality, despite being mathematically allowed by the equations of special relativity. The principle of causality, which requires that causes must precede their effects, seems to be more fundamental than the mathematical possibility of faster than light particles. However, tachyons have played important roles in theoretical physics as tools for exploring the boundaries of what is possible within relativistic frameworks. They help physicists understand why the light speed barrier exists and what would happen if it could be violated. They also appear in certain advanced theories of quantum mechanics and particle physics, though always in contexts where they either cannot be directly observed or where their problematic properties are somehow avoided. In quantum field theory, tachyonic fields sometimes appear in the mathematical description of unstable systems. These tachyonic modes do not represent actual faster than light particles, but rather indicate that the system is unstable and will evolve toward a more stable configuration. The presence of tachyons in the mathematics signals that the current state of the system cannot persist and must change into something else. For example, in the Higgs mechanism that gives mass to elementary particles, the Higgs field initially appears to have tachyonic mass. This does not mean that faster than light particles are involved, but rather that the field is unstable in its initial configuration and must settle into a lower energy state. When it does so, the tachyonic instability disappears and is replaced by ordinary massive particles. Some theories of gravity and cosmology also involve tachyonic fields in their mathematical descriptions. These fields can drive accelerated expansion of space, potentially explaining phenomena like cosmic inflation in the early universe, or the current acceleration of cosmic expansion attributed to dark energy. Again, these are not faster than light particles in the usual sense, but rather fields whose mathematical properties resemble those of tachyons. The search for actual tachyonic particles has been ongoing for decades, with researchers looking for any evidence of faster than light motion in cosmic ray events, particle accelerator experiments, and astronomical observations. Some experiments have claimed to detect particles traveling faster than light, but these results have always been explained by experimental errors or misinterpretations of the data. The most famous case occurred in 2011 when researchers at the OPERA experiment in Italy announced that they had detected neutrinos traveling faster than light. This result, if confirmed, would have represented one of the most significant discoveries in the history of physics, potentially requiring a complete revision of our understanding of space-time and causality. However, subsequent investigation revealed that the faster-than-light measurement was due to a loose fiber optic cable in the timing system that was introducing systematic errors into the measurements. When the cable was properly connected, the neutrinos were found to travel at exactly the speed expected from relativity theory, confirming once again that nothing travels faster than light. This episode illustrates both the excitement that any potential discovery of faster-than-light travel would generate and the extreme care that must be taken when measuring phenomena at the limits of experimental precision. The scientific community was appropriately skeptical of the OPERA result because it would have violated such fundamental principles of physics. The theoretical study of tachyons has also led to insights about the nature of information and communication in relativistic systems. Even if tachyons existed, it might not be possible to use them to send meaningful information faster than light. The quantum mechanical properties of tachyons might prevent them from carrying organized signals, or the process of detecting them might introduce delays that eliminate any faster than light advantage. Some theories suggest that tachyons might exist, but be fundamentally undetectable by ordinary matter. They might interact so weakly with bradyonic matter that they pass through our detectors without leaving any trace. In such scenarios, tachyons could permeate the universe without affecting causality or violating any observed physical laws. Another possibility is that tachyons might exist only in higher dimensional spaces that are inaccessible to our three-dimensional experience. In string theory and other advanced theoretical frameworks, particles can have properties that extend into additional spatial dimensions. Tachyonic behavior might be possible in these higher dimensional spaces while remaining unobservable in our familiar three-dimensional world. The mathematical exploration of tachyons has also contributed to our understanding of the deep connections between space, time, and causality. By studying what would happen if faster-than-light travel were possible, physicists have gained insights into why the light-speed barrier exists and how it protects the logical consistency of physical law. Tachyons represent the ultimate expression of what it might mean to go beyond light speed. If ordinary matter approaching light speed experiences infinite time dilation and length contraction, tachyons would experience these effects in reverse. Time would flow backward. Distances would become imaginary, and the normal relationships between cause and effect would be inverted. This creates a picture of tachyonic existence that is so alien to our experience that it challenges our ability to even conceive of what such particles would be like. They would inhabit a realm where faster motion requires less energy, where time flows backward, where causality is reversed, and where the normal logic of physical processes breaks down completely. The fact that such particles are mathematically possible, but apparently do not exist in nature, tells us something profound about the universe we inhabit. The cosmos seems to be constructed in such a way that it protects itself from the logical paradoxes that faster-than-light travel would create. The light-speed barrier is not just a speed limit, but a fundamental feature of reality that preserves the rational structure that makes science possible. Whether tachyons exist or not, their theoretical possibility illuminates the boundaries of the possible and helps us understand why those boundaries exist. They show us what the universe would be like if the light speed barrier could be violated. And in doing so, they help us appreciate why that barrier is so important for maintaining the logical consistency of the world we observe. We have explored how physical objects behave at light speed and discovered that massive particles can never reach this cosmic limit, while massless particles must always travel at this speed. But what about more abstract concepts like consciousness, information, or the act of observation itself? Could these non-physical phenomena somehow transcend the limitations that apply to matter and energy? Could mind or information ride alongside light in ways that physical objects cannot? These questions touch on some of the deepest mysteries in physics and philosophy, connecting the hard limits of relativity with fundamental questions about consciousness, information theory, and the nature of observation in quantum mechanics. The answers reveal surprising connections between the cosmic speed limit and the very foundations of knowledge, thought, and awareness. Let us begin with the concept of information, which plays a central role in modern physics. Information, in the technical sense used by physicists, refers to any pattern or correlation that can distinguish between different possible states of a system. It might be the pattern of bits stored in a computer memory, the sequence of nucleotides in a DNA molecule, or the quantum state of a particle that has been measured in an experiment. At first glance, information might seem like an abstract concept that could transcend physical limitations. After all, information is not made of matter or energy in any direct sense. It is pattern, organization, correlation. Could such abstract entities somehow move faster than light, even if the physical systems that carry them cannot? The answer, somewhat surprisingly, is no. Information must follow the same relativistic rules that govern matter and energy. This principle, known as the no-communication theorem in quantum mechanics, states that information cannot be transmitted faster than light by any known physical process. The cosmic speed limit applies not just to particles and waves, but to information itself. To understand why this is the case, we need to recognize that information cannot exist independently of physical systems. Every piece of information must be encoded in some physical substrate, whether it is the position of particles, the polarization of photons, the spin of electrons, or the configuration of atoms in a crystal. Since these physical carriers are subject to relativistic limitations, the information they carry is also limited by the speed of light. Consider what happens when you try to send information from one location to another. Whether you use radio waves, laser pulses, electrical signals, or even quantum entanglement, the information must be carried by physical processes that respect the light speed barrier. A radio signal propagates at light speed through electromagnetic waves. A laser pulse travels at light speed through photons. An electrical signal moves through wires at speeds determined by the electromagnetic properties of the conducting material, which cannot exceed light speed. Even more exotic possibilities for information transmission run into the same fundamental limitations. Quantum entanglement, often misunderstood as providing faster-than-light communication, actually cannot be used to send information faster than light. While entangled particles do exhibit instantaneous correlations across arbitrary distances, these correlations cannot be used to transmit controllable information without additional classical communication that is limited by light speed. The deeper reason why information cannot travel faster than light relates to the concept of causality. Information represents a form of influence that one system can have on another. If information could travel faster than light, it would be possible for effects to precede their causes, leading to logical paradoxes that would undermine the rational structure of physics. This connection between information and causality becomes even more important when we consider the role of information in consciousness and observation. Every act of perception, every thought process, every conscious decision involves the processing and transmission of information within the brain and nervous system. Since this information is physically embodied in neural activity, it must respect the same speed limits that govern all other physical processes. The implications for consciousness are profound. Your thoughts, perceptions, and awareness are all forms of information processing that occur through physical mechanisms in your brain. The electrical and chemical signals that carry information between neurons travel at speeds far below light speed, typically measured in meters per second, rather than the 300 million meters per second of light. This means that consciousness itself is fundamentally limited by the speed of light, though in practice it operates at much slower speeds determined by the biology of neural transmission. Your awareness cannot transcend the relativistic limits that govern all information processing. There is no way for your consciousness to somehow ride alongside light or to experience the timeless realm that photons inhabit. But what about the act of observation in quantum mechanics, which seems to play such a special role in determining physical reality? In quantum theory, the act of measurement appears to cause the collapse of the wave function, selecting a specific outcome from the range of possibilities described by quantum superposition. Could this mysterious process somehow operate faster than light, or outside the normal constraints of relativity? The answer is again no, though the reasons are subtle and touch on some of the deepest issues in the interpretation of quantum mechanics. The measurement process in quantum mechanics is ultimately a physical interaction between the measuring device and the quantum system being observed. This interaction must respect all the usual rules of relativity, including the prohibition against faster-than-light information transmission. While quantum correlations can be established instantaneously across arbitrary distances through entanglement, the process of measurement and the communication of measurement results are still limited by light speed. An observer on one side of an entangled system cannot determine what measurement was performed on the other side without receiving classical information about that measurement, and this classical information cannot travel faster than light. The apparent instantaneous nature of quantum measurement reflects the non-local correlations built into entangled quantum states, but it does not allow for faster than light communication or information transfer. The quantum measurement process operates within the constraints of relativity, even though it exhibits phenomena that seem to transcend classical intuitions about locality and causality. This has important implications for any hypothetical observer trying to ride alongside light. Even if such an observer could somehow exist at light speed, they would be unable to make meaningful measurements or observations. The physical processes required for observation, including the interaction between light and matter that makes vision possible, require time to unfold. In the timeless realm of light speed, there would be no opportunity for the causal interactions that make observation possible. Furthermore, any measuring device or conscious observer operating at light speed would face the same problems that prevent any massive object from reaching this velocity. The infinite energy requirements, the complete time dilation, and the breakdown of normal causality would make it impossible for any information processing system to function at light speed. The concept of riding alongside light also faces challenges from the perspective of information theory and computation. Every computation, every logical operation, every act of information processing requires time to complete. Logical gates must switch states, memory must be accessed and updated, and signals must propagate through computational networks. All of these processes require finite amounts of time and cannot be compressed to zero duration. In the timeless realm of light speed, computation becomes impossible. There is no time for algorithms to execute, no opportunity for logical operations to complete, and no possibility for the sequential processing that underlies all forms of information manipulation. A hypothetical observer traveling at light speed would be unable to think, compute, or process information in any meaningful way. This connects to fundamental limits in computational theory related to the thermodynamics of information processing. Every computation requires the expenditure of energy and the production of entropy. processes that must unfold over finite time intervals. The Landauer limit, a fundamental principle in computational physics, states that erasing information requires a minimum amount of energy and produces a minimum amount of heat. These thermodynamic processes cannot be compressed to zero time, which means that computation is incompatible with light-speed existence. The relationship between information and physical reality becomes even more complex when we consider the role of information in defining the structure of space-time itself. In some interpretations of quantum gravity and cosmology, information plays a fundamental role in determining the geometric properties of space and time. The holographic principle, for example, suggests that all the information contained in a volume of space can be encoded on its boundary, creating deep connections between information theory and the structure of space-time. If information is indeed fundamental to the structure of reality, then the limitations on information transmission may reflect even deeper principles about the nature of space and time. The light-speed barrier might not just be a speed limit imposed on matter and energy, but a fundamental feature of how information and reality are related to each other. These considerations also have implications for artificial intelligence and the possibility of uploading consciousness to computational systems. If consciousness is fundamentally a form of information processing, then any artificial system that could support consciousness would face the same relativistic limitations that apply to biological brains. There would be no way to create a conscious artificial intelligence that could somehow transcend the light-speed barrier or exist in the timeless realm of photons. The search for faster-than-light information transmission has been ongoing for decades, with researchers exploring exotic possibilities like closed time-like curves, wormholes, and quantum teleportation. However, every proposed mechanism either violates known physics, requires exotic matter with impossible properties, or fails to actually transmit information faster than light when analyzed carefully. Quantum teleportation, for example, can transfer the quantum state of a particle instantaneously across arbitrary distances, but it requires classical information about the measurement results to be transmitted at light speed or slower. The teleportation process cannot be completed until this classical information arrives, which means that no information travels faster than light overall. Similarly, theoretical proposals for faster-than-light travel through space-time manipulation, such as the Alcubierre warp drive, face enormous challenges related to energy requirements and causality violations. Even if such technologies were somehow possible, they would not allow consciousness or information to transcend the fundamental limitations imposed by the structure of space-time. The conclusion is clear. Consciousness, information, and observation are all fundamentally limited by the same cosmic speed limit that governs matter and energy. There is no way for mind, thought, or awareness to ride alongside light, or to transcend the relativistic constraints that define the structure of our universe. The timeless realm of light speed remains forever inaccessible to any form of consciousness or information processing system that we can imagine or construct. After journeying through the strange landscape of relativistic physics, exploring the behavior of matter and energy at cosmic speeds, and investigating the deepest principles that govern our universe, we arrive at the final answer to our original question. Can you ride a beam of light and still exist? The conclusion is both definitive and profound. To ride light is to cease existing in any meaningful sense of the word. This is not merely a limitation of current technology or a temporary obstacle that might be overcome by future scientific advances. It is a fundamental feature of the universe itself, built into the very structure of space, time, matter, and energy. The impossibility of riding light while maintaining existence reveals deep truths about what it means to be, to experience, to think, and to exist as a conscious entity in our cosmos. Let us summarize the insurmountable barriers that prevent any conscious being from riding alongside light. Each barrier alone would be sufficient to make such a journey impossible, but together they create an absolute prohibition that cannot be circumvented by any conceivable means. The first and most fundamental barrier is the infinite energy requirement. As we have seen throughout our exploration, accelerating any object with mass toward light speed requires ever-increasing amounts of energy. The mathematical relationship is unforgiving. To reach exactly light speed would require infinite energy, which is simply not available anywhere in the universe. No conceivable power source, no matter how advanced, could provide the infinite energy needed to accelerate a human being or any massive object to light speed. This energy barrier is not a practical limitation that might be solved with better engineering. It is a mathematical impossibility built into the equations that govern the universe. Even if you had access to all the energy contained in all the stars, in all the galaxies in the observable universe, it would still not be enough to accelerate a single atom to exactly light speed. The energy requirement becomes infinite at the cosmic speed limit, creating an absolute wall that cannot be breached. The second insurmountable barrier is the complete collapse of time itself. As velocity approaches light speed, time dilation becomes infinite. At exactly light speed, time stops completely from the perspective of outside observers. But more critically, the very concept of proper time, the time experienced by a traveling object, becomes meaningless for anything moving at light speed. Without the passage of time, existence becomes impossible. Consciousness requires time to think, to process information, to experience sensations, and to maintain the continuity of awareness that defines conscious existence. Biological processes require time to function. Chemical reactions require time to proceed. And physical interactions require time to unfold. In the timeless realm of light speed, none of these processes can occur. You cannot think without time, because thinking is fundamentally a temporal process. Neural signals must propagate through your brain, synapses must fire in sequence, and memories must be accessed and processed. All of these activities require finite amounts of time to complete. In a realm where no time passes, thought becomes impossible, consciousness ceases to function, and awareness simply stops. The third barrier is the complete breakdown of spatial relationships. Length contraction becomes infinite at light speed, compressing distances to zero in the direction of motion. Your body, your spacecraft, and indeed your entire relationship to space would collapse to nothing. The concept of spatial extent, which is fundamental to the existence of any physical object, becomes meaningless at the cosmic speed limit. Without spatial extent, physical existence becomes impossible. Your atoms could not maintain their structure, your molecules could not exist, and your body could not have any definable form. The material basis of your existence would be compressed out of reality itself. You would not simply become very small, you would cease to have any spatial existence whatsoever. The fourth barrier is the absence of a valid reference frame. As we explored in our discussion of photons, objects traveling at light speed do not have reference frames in the same sense that slower moving objects do. The mathematical framework of physics simply breaks down when applied to light speed observers. There is no consistent way to define what the universe would look like from the perspective of something traveling at light speed. This is not a limitation of our current understanding that might be resolved with better theories. It is a fundamental feature of the geometric structure of space-time itself. The equations of relativity, which have been tested and confirmed in countless experiments, simply do not allow for the existence of light-speed reference frames. The mathematics that describes motion through space and time becomes undefined and meaningless at the cosmic speed limit. The fifth barrier relates to causality and the logical structure of reality. At light speed, the normal relationships between cause and effect break down completely. Events that should be separated in time becomes simultaneous, and the sequential ordering that gives meaning to physical processes disappears. The logical framework that allows consciousness to make sense of experience and to maintain coherent thoughts requires a clear distinction between past, present, and future. At light speed, these distinctions vanish. Without causality, coherent existence becomes impossible. You could not form memories because there would be no meaningful distinction between the moment a memory is formed and the moment it is recalled. You could not make decisions because there would be no temporal separation between the consideration of options and the selection of an action. The entire framework of conscious experience depends on the ordered flow of time and the preservation of causal relationships. The sixth barrier involves the fundamental nature of information processing. As we have established, consciousness requires the processing and transmission of information within the brain and nervous system. But information cannot exist independently of physical substrates, and these physical carriers are subject to all the same relativistic limitations that apply to matter and energy. At light speed, information processing becomes impossible because there is no time for signals to propagate, no opportunity for computations to complete, and no possibility for the sequential operations that underlie all forms of cognition. The neural networks that support consciousness require finite amounts of time to function, and this requirement cannot be satisfied in the timeless realm of light speed. Even if we imagine some exotic form of consciousness that does not rely on biological neural networks, it would still require some physical substrate for information processing. Whether based on electronic circuits, quantum systems, or entirely hypothetical technologies, any information processing system must respect the fundamental limits imposed by relativity and thermodynamics. These limits make consciousness incompatible with light-speed existence. The seventh and perhaps most profound barrier is the fundamental incompatibility between existence and the timeless realm that photons inhabit. To exist means to persist through time, to maintain identity across temporal intervals, to experience duration and change. These basic features of existence are impossible in a realm where no time passes. Photons do not exist in the same sense that massive objects exist. They are excitations of quantum fields that connect events across space without experiencing the journey between them. A photon emitted by a distant star and absorbed by your eye after traveling for millions of years experiences its entire journey as a single, instantaneous event. There is no sense in which the photon exists during its journey, because there is no time during which it could exist. To ride alongside light would mean entering this timeless realm and abandoning existence as we understand it. You would not experience the journey because there would be no time in which experience could occur. You would not arrive at your destination because arrival implies a temporal process. You would simply cease to exist in any meaningful sense, becoming a mathematical abstraction rather than a conscious being. The eighth barrier involves the quantum mechanical nature of reality at the most fundamental level. Quantum mechanics describes matter and energy in terms of wave functions that evolve over time according to the Schrödinger equation. This evolution requires time to unfold, and the probabilistic nature of quantum measurements requires temporal processes to determine outcomes. At light speed, where time stops completely, quantum evolution becomes impossible. Wave functions cannot evolve, measurements cannot be completed, and the quantum processes that underlie the behavior of atoms and molecules cannot occur. The quantum foundation of matter and energy breaks down completely at the cosmic speed limit, making any form of material existence impossible. These barriers are not independent obstacles that might be overcome one by one through clever engineering or advanced technology. They are interconnected aspects of a single, fundamental truth about the structure of our universe. The cosmic speed limit is not an arbitrary restriction, but a necessary feature of reality that preserves the logical consistency of space, time, matter, energy, and consciousness. The universe protects itself from the paradoxes and impossibilities that would arise if conscious beings could travel at light speed. The infinite energy requirements, the collapse of time and space, the breakdown of causality, and the impossibility of information processing all serve to maintain the boundary between the realm of ordinary existence and the strange physics of the ultimate speed limit. Understanding why you cannot ride light while still existing illuminates fundamental truths about the nature of consciousness, existence, and reality itself. Consciousness is not a disembodied phenomenon that can transcend physical limitations. It is intimately connected to the material processes that support it, and these processes are subject to the same cosmic constraints that govern all matter and energy. Existence requires time, space, causality, and the ability to process information. All of these requirements are violated at light speed, making conscious existence impossible at the cosmic speed limit. To truly understand what it would mean to ride light, we must recognize that it would mean ceasing to exist as conscious beings and entering a realm that lies beyond the boundaries of normal experience. The impossibility of riding light while maintaining existence is not a limitation of human understanding or technology. It is a fundamental feature of the universe that reflects the deep connections between consciousness, physics, and the structure of reality itself. The cosmic speed limit serves as the boundary between existence and non-existence, between the temporal realm of conscious experience and the timeless realm of pure physics. In recognizing this boundary, we gain a deeper appreciation for the remarkable nature of consciousness and existence. We are beings of time and space, products of a universe that allows for the complex information processing that makes awareness possible. The fact that we can contemplate riding alongside light, even though we cannot achieve it, reveals the extraordinary nature of conscious thought and the privileged position that awareness occupies in the cosmic order. Our journey through the physics of light-speed travel has taken us to the very edge of existence itself, revealing truths about reality that are both beautiful and profound. We began with a simple question that has captivated human imagination for over a century. What would it be like to ride alongside a beam of light? The answer we have discovered is both definitive and deeply philosophical. To ride light is to cross the boundary between being and nothing, between existence and the void that lies beyond conscious experience. Light occupies a unique and privileged position in our universe. It serves as the cosmic messenger, carrying information across vast distances and connecting events separated by billions of years. Light from distant stars brings us knowledge of the deep past, while light from nearby objects creates our immediate sensory experience of the present moment. Without light, the universe would be disconnected, with no way for distant regions to influence each other or for conscious beings to perceive the world around them. But light is more than just a messenger. It defines the fundamental structure of space-time itself, establishing the maximum rate at which cause can create effect and information can travel from one location to another. The speed of light is not merely the velocity of electromagnetic radiation, but the cosmic speed limit that governs all physical processes, from the smallest quantum interactions to the largest cosmic phenomena. This speed limit creates a profound division in the universe between two fundamentally different realms of existence. On one side lies the temporal realm where we live, where time passes and change is possible, where consciousness can emerge and flourish. This is the realm of massive particles that must always travel slower than light, where clocks tick and memories form, where cause precedes effect and the future remains open to possibility. On the other side lies the timeless realm of light itself, where photons exist in an eternal present moment that connects all of space instantaneously. This is a realm without duration, without sequence, without the temporal flow that makes conscious experience possible. It is a realm of pure connection, where emission and absorption are the same event, where the journey across billions of light years occupies no time at all. The boundary between these two realms is absolute and cannot be crossed by any conscious being. To approach this boundary is to experience the strange effects of relativity, time slowing down, space contracting, energy requirements soaring toward infinity. But to actually cross the boundary would be to leave existence behind entirely, to enter a realm where consciousness cannot function and awareness cannot persist. This boundary is not an accident or arbitrary limitation. It is a necessary feature of our universe that preserves the logical consistency of physical law and protects the conditions that make consciousness possible. If conscious beings could travel at light speed, the causal structure of space-time would break down, causality would be violated, and the rational order that allows science and logic to make sense of the world would collapse. The universe protects itself from such paradoxes through the mathematical structure of relativity, which makes light speed travel impossible for anything with mass, while preserving light speed as the realm of massless particles and pure information transfer. This protection mechanism ensures that consciousness remains confined to the temporal realm where it can function, while allowing light to serve its crucial role as the universal messenger that connects all regions of space and time. Understanding this cosmic architecture reveals something profound about our place in the universe. We are creatures of time, beings whose very existence depends on the passage of temporal moments and the unfolding of causal sequences. Our thoughts require time to form. Our memories require time to encode and retrieve. And our awareness requires the continuous flow of experience through temporal intervals. This temporal nature of consciousness is not a limitation, but a gift. It allows us to experience growth and change, to form new memories and learn from past experiences, to anticipate the future and work toward goals that give meaning to our existence. The flow of time that prevents us from riding light is the same flow that makes consciousness, creativity, and purpose possible. Yet even though we cannot ride light, we can chase it. We can build spacecraft that approach ever closer to the cosmic speed limit, experiencing the strange and beautiful effects of relativistic travel. We can explore the universe through the light that reaches us from distant stars and galaxies, using photons as our cosmic messengers to probe the deepest mysteries of space and time. Every time we look up at the night sky, we are participating in a kind of light speed travel, allowing photons that have journeyed across vast cosmic distances to enter our eyes and create images in our minds of distant realms. The light from the nearest star carries information about events that happened over 4 years ago. The light from distant galaxies shows us the universe as it appeared billions of years in the past. In this sense, light serves as our time machine, allowing us to see across cosmic history without ever leaving our earthly reference frame. We cannot ride light, but we can receive its messages, decode its information, and use it to construct our understanding of the universe and our place within it. The impossibility of riding light while maintaining existence also illuminates the remarkable nature of the conscious experience we do possess. Every moment of awareness, every thought and sensation, every memory and emotion represents a triumph over the fundamental tendency of the universe toward entropy and disconnection. Consciousness creates order from chaos, meaning from randomness, and purpose from the raw material of physical law. The fact that consciousness exists at all in a universe governed by relativistic physics is extraordinary. The delicate balance of forces and constants that allows matter to form stable structures, stars to shine for billions of years, planets to maintain stable orbits, and complex chemistry to emerge and evolve, is precisely what enables consciousness to arise and flourish in the temporal realm below light speed. We are the universe becoming aware of itself, matter and energy, organized in such complex patterns that they can contemplate their own existence and probe the fundamental laws that govern reality. The light speed barrier that prevents us from riding alongside photons is the same barrier that preserves the conditions necessary for this remarkable emergence of consciousness from inanimate matter. In our exploration of light speed travel, we have discovered that the universe operates according to principles that are both stranger and more beautiful than everyday experience suggests. Space and time are flexible and relative. Matter and energy are interchangeable, and the cosmic speed limit connects seemingly unrelated phenomena in ways that reveal the deep unity underlying physical law. These discoveries have practical implications for our future as a species. While we may never be able to travel at light speed, we can aspire to travel at significant fractions of this cosmic limit, opening up the possibility of interstellar exploration and the expansion of human consciousness beyond our home planet. Even at more modest relativistic speeds, the effects of time dilation could allow human explorers to journey to distant stars within their lifetimes, though they would return to find that much more time had passed on Earth. The universe is vast beyond comprehension, filled with billions of galaxies, each containing billions of stars, many of which are likely surrounded by planets where the conditions for consciousness might arise. Light connects all of these distant realms, carrying information across cosmic distances and maintaining the causal relationships that allow the universe to function as a coherent whole. We cannot ride light and still exist, but we can follow its lead in connecting distant regions of space and time through the power of consciousness and imagination. We can use the messages that light brings us to construct ever more complete pictures of cosmic reality, and we can send our own light signals out into the universe as messages to any other conscious beings who might be listening. You can chase light forever. You can get closer and closer to its cosmic realm, experiencing the strange effects of relativistic travel and gaining insights into the fundamental nature of space and time. You can push the boundaries of what is possible for conscious beings, exploring the limits of existence in the temporal realm where awareness can flourish. But to become light, to ride it across the cosmos, is to give up existence itself. Light does not journey through time in the way that conscious beings experience temporal flow. Light simply connects, linking moments of emission with moments of absorption across arbitrary distances of space without experiencing the passage of time between them. And you, as a creature of time and consciousness, must let light pass. You must remain in the temporal realm where thoughts can form, memories can accumulate, and awareness can persist through the flowing moments that give meaning to existence. The boundary between being and nothing is not a limitation to be overcome, but a fundamental feature of reality that preserves the conditions necessary for consciousness to emerge and thrive in our extraordinary universe.